Hello. I have to warn you, the presentation is a little bit weird.
Weird in the way that we'll have seizures first? Or?
It's mostly pictures. The text is on the paper. So I'm Dimitris, I am coming from Greece. I'm a researcher at the Athens University of Economics and Business. First of all, I would like to thank you for giving me the opportunity to come here and present you our work. Together we will discuss about the evolution of security bugs. Now in general, a software bug, as you probably know, is a programming error that can affect either the performance of a program, its functionality, or violate its coding practices. Now, a security bug is a programming error that introduces a potentially exploitable weakness into a computer system. This weakness could lead to a security breach with unfortunate consequences. Now, compared to other bug categories, failures due to security bugs have two distinct features. One, they can severely affect an organization's infrastructure. Specifically, whereas a software bug can cause a software artifact to fail, a security bug can allow a malicious user to alter the execution of the entire application for his or her own gain. Two, they can cause significant financial damage to an organization. Security bug disclosures lead to a negative and significant change in market value for a software vendor. Hence, one of the basic pursuits in every new software release should be to mitigate such bugs. The aim of our work was to study the characteristics and the behavior of security bugs in relation to evolving software packages. I wish that this figure was mine, but it's Michael Gousios. It's the evolution storyline of Apache. In particular, we inspected project releases to check if security bugs decrease or increase over time. In this case, our hypothesis was that they should decrease because of their criticality. Then, we examined security bug persistence across releases. Our expectation was that security bugs should be eliminated earlier than other bugs. Then we studied the relation between security bugs and the project release's size. Our hypothesis here was that security bugs are proportional to a project release's size. Finally, we examined the correlation of security bugs with other categories. Our expectation was that security bugs appeared together with bugs coming from other categories. Focusing on the evolution of such bugs is not a new idea. Most of the previous related work done involved the observation of a small number of projects. Contrary to this, for our analysis, we used a large software ecosystem that contained thousands of versions of interdependent projects. Specifically, for our experiment, we used the public Maven repository that contains approximately 265 gigabytes of data. Now, Maven is a build automation tool used primarily for Java projects. To build a software component, it dynamically downloads Java libraries and Maven plugins from their central repository, which is the one that we used. In this figure, you can see the Maven repository hierarchy. A group ID represents a project. A project can have multiple modules that are represented by artifact IDs. Every artifact can have different versions in the repository. A project version can be uniquely identified by the triplet group ID, artifact ID, and version. Keep in mind that in the Maven repository, versions are actual releases. As a result, we do not have we do not have an indication of how many changes have been made between the releases. In essence, these versions were the ones that were or still are out there in the wild, being used either as applications or dependencies of others. Here we can see some descriptive statistic measurements for the repository. The measurements indicate that there are 17,505 projects and the dataset's median is 3. This means that almost 50% of the project population have 1 to 3 versions. Typically, most projects have a few number of versions, but there are some projects with 10 versions and only a few with hundreds of versions. The maximum number of versions for a project is 338. The third quartile measurement also indicated that 75% of the projects have a maximum of 8 versions. To statically analyze all the releases, we used Findbugs, which is a tool that has already been used in research and examines bytecode to detect software bugs. This came in handy since Maven contains all project versions in the form of jars. We have to mention here, as a threat to the validity of our experiment, that a static analysis tool like this can produce false positive or negative alarms. Before performing our experiment and collect the metric results of the Findbugs tool, we scanned the Maven repository for appropriate jars and created a series of processing tasks that included a jar's name and added them to a task queue mechanism. The fourth entity involved in our experiment, apart from the repository, the static analysis tool, and the task queue mechanism, was a custom Python script that we will call the worker from now on. Here you can see the data processing architecture of our experiment. As you can see, workers can actually run at the same time. In our case, 25 Unix-based workers run simultaneously. A typical processing cycle of a worker included the following steps. After the worker spawned, it requested a task from the queue. This task contained the jar name, which was typically a project version that was downloaded locally. First, specific jar metadata were calculated and stored. Such metadata included the project size, its dependencies, and the number that represented the chronological order of the release. Then, Findbugs was invoked by the worker, and its results were also stored in the data repository. When the task was completed, the queue was notified, and the next task was requested. Before presenting our analysis and results, let's talk a little bit about the bug categories that Findbugs reports. Here you can see some of the basic bug categories. 2 of them, namely security and malicious code, involve security-related bugs. Now, let's see some primary observations concerning the software defects of the Maven repository as a whole. Our first result concerns the most popular bugs in the ecosystem. Together with the bad practice bugs and the style bugs, security bugs are the most popular. This we call security bugs here the sum of the 2 aforementioned categories.
Did you say what an experimental bug is?
The experimental bug category, sorry. Yeah. The experimental bug category contains uncategorized bugs.
Is malicious here grouped in with security? Malicious was
Oh.
on your previous list, but it's not here.
Yes. Here, security bugs.
It's both.
Yeah, it's the sum of those two categories. Only here we'll see what there's a subcategorization now that we will discuss. This could be an indication that programmers write code that implements the required functionality without considering its many security aspects, which is an issue that has already been reported in literature. For our further analysis, we created some more subcategories. This is mainly for the following reasons. First, the malicious code category contains, for the most part, bugs that imply violations of good object-oriented programming design. Also, we wanted to distinguish bugs that we could call severe. Such bugs are related to vulnerabilities that appear due to the lack of input validation and can lead to damaging attacks like code injection, SQL injection attacks, and cross-site scripting. These kind of attacks are currently topping the corresponding lists of most security providers. Also, as the bug descriptions on the Find Bugs page indicate, if an application has such bugs, it might have more vulnerabilities that Find Bugs doesn't report. As a result, we created a subcategory containing bugs of this kind, which is a subset of the security category, and we call it security high, meaning with high severity. The remaining bugs of the security category are grouped together with the bugs of the malicious code category in another one that we call security low. This table presents the number of releases where at least one security high bug exists. In essence, 5,501 releases, which is approximately 4.77%, contained at least one severe security bug. Given the fact that other projects include these versions as their dependencies, they are automatically rendered vulnerable if they use the code fragments that include these defects. Now, Linus' law states that given enough eyeballs, all bugs are siloed. In a context like this, we expected that the project versions that are dependencies to many other projects would have a small number of security bugs. To achieve this, we created a graph that represented the snaps of the Maven repository. The nodes of the graph represented the versions, and the vertices, their dependencies. Keep in mind that because of some missing information from some projects, the graph was not entirely accurate, meaning dependencies pointing out to a project rather than a version. And also, it was not complete. There were missing versions mentioned as dependencies. After creating the graph, we ran the PageRank algorithm on it and retrieved all PageRanks for every node. Then we examined the security bugs of the 15 most popular nodes based on their PageRank. Contrary to Linus' law, 33 of them contained bugs coming from the security low subcategory, while 2 of them contained security high bugs. Keep in mind that 25 of them were latest versions at the time. Our first key finding involved how security bugs evolve over time. The relation between bugs and time can be traced from the number of bugs per category in each project version. In particular, we calculated the correlations between the defects count and the ordinal version number across all projects to see if bigger versions relate to higher or lower defect counts. As you can see, even if the tendency is for defect counts to increase, This tendency is extremely slight. This tendency, though, applied to all versions of all projects together. The situation was different when we performed correlations between bug counts and version ordinals in individual projects. The horizontal axis in this chart presents the correlations, while the vertical axis the number of projects. Note here that scale is logarithmic. The spike in point 0 is explained by the large number of projects for which no correlation could be established. Still, we can see that there were projects where a correlation could be established, either positive or negative. The security high category, as you can see at the top or left of the slide, is particularly bimodal. But this is explained by the small number of correlations that could be established, 9 in total. Yeah.
This is correlation between version number and number of security.
Yeah, defect counts. Until now, contrary to our hypothesis, we cannot say that across project defect counts increase or decrease significantly across time. However, as you can see here, in individual projects, defect counts can have a strong upwards or downwards tendency. This is a histogram. This is a histogram of the changes of differing bug counts in project versions. The horizontal axis represents the number of bugs, while the vertical, the number of transitions, regardless the project. In most cases, a bug count does not change between versions, but when it does change, it may change upwards or downwards. Note also the spectacular changes of introducing or removing large numbers of defects. This may be the result of doing and undoing a pervasive code change that runs foul of some bug identification rule. Our next finding involves the relation of defects with the size of a jar. To achieve this, we carried out correlation tests between the size and the defect counts for each project conversion. As you can see in this table, the security high category stands out by having a remarkably lower effect than the other categories, contrary to our hypothesis. Recall that bugs that belong to the security high category are related to user input validation issues. This could be an indication that even if a programmer adds code to a new version, if this code does not require user input, the possibility of such bug is minimal. Now, to examine the relation between the persistence of different kinds of bugs and of security bugs in particular, we used as a persistence indicator the number of versions a bug remains open in a project. There is an interesting table that can be found on the paper that shows our findings in detail, but it's huge, and I don't think that it is useful to present it here. What I want you to keep is that contrary to our expectation in all categories, including the security high, a bug persists on average between 2 and 3 versions, with a difference being in the decimal digits. Finally, to see whether bugs flock together, we performed pairwise correlations between all bug categories. Specifically, we calculated the correlations between the number of distinct bugs that appeared in a project throughout its lifetime. In this figure, you can see the results of this analysis. The thinner the ellipse, the stronger the association. As you can see, our results show that, in general, bugs do flock together. We did not find projects with only a certain kind of bug. Bugs seem to come upon projects in swarms of different kinds. But bugs of the security high category are different. They are either not associated with other bugs or only weakly so. Perhaps it takes a special kind of blunder to make it a security hazard. Thus, to find such defects, code reviewers with experience in software security issues might be needed. Now, let me close my presentation with some observations regarding the results in the experiment. Even if we did not find if defect counts increase or decrease over time, the fact that projects have their own idiosyncrasies concerning security bugs could help us answer questions like, what are the common characteristics of a project where security bugs increase over time? In addition, by examining source code repositories more closely, we could see how different development styles, for instance, size of commits or number of developers, affect projects. Finally, by selecting a large ecosystem that includes applications written only in Java, we excluded by default measurements that involve vulnerabilities related to the C programming language, like the infamous buffer overflow effects. This is because Java enforces bound checking at runtime. Still, by examining software artifacts with similar characteristics facilitates the formation of an experiment like this. Thus, future work on our approach could also involve the observation of other ecosystems that serve different languages in the same manner. You can find the data and code that we used for our experiment online at the following address. The URL is also mentioned in the paper. So, thank you.
Thank you. We'll take questions. Did you want people to use the microphone then? Oh, that was all right. Oh, that was.
Yeah, I have two questions. What you described sounds similar to something that Ram Chilaraji did, I don't know, 10 or 15 years ago, called orthogonal defect classification. So if you're aware of that paper, I just wondered if you would characterize your work as similar or how it would be different from what Chilaraji did in that paper. And the second question is, you mentioned something about threats to validity, but I didn't quite hear what you said the threats were. I wonder if you could just repeat that.
Yeah, of course. Concerning the first question, the related group that you mentioned had to do with the categorization, you said, or the evolution?
So, well, are you familiar with the Chilaraji paper called orthogonal defect classification? Because if you're not familiar, then there's kind of like no question.
Okay.
Okay, so then we'll just go to the, I think it was quite similar work actually. He did that while he was at IBM. I don't know, Carl, you remember that paper?
Yeah, I remember the paper.
Am I on track here that there's a similarity?
I'd have to look at that paper again. I haven't
Okay.
looked at it on that.
I think there is, but, and Michelle would know about this, I think. In any case, what about the threats to validity? I just didn't hear what you said.
And one threat to validity that I mentioned was that a static analysis tool like FindBugs can produce false positive or negative alarms. So this is technically a threat to validity to the whole experiment.
Okay, so that is kind of what I remember you saying, but what I don't understand is which concept of validity is being violated by that particular threat. And I asked that question because while I agree that what you said is probably true, it does not strike me as a threat to validity.
You mean that it's not a threat to validity?
I don't see it, right? So I'm asking you to help me understand why it's a threat to validity, right? So there must be some validity principle that's being violated here, and I guess you must know what that is. Or
Because
or you wouldn't have said.
Yeah. If you find an SQL injection security error or bug, in a project that does not require input. This is a false positive alone that affects the whole experiment. It's wrong. So,
might you characterize it as that it has to do with, kind of relative to what Seth was saying this morning, have to do with error bars that might show?
Well, so broadly, there are two categories of validity. One is internal and the other one is external.
Okay.
Right? And there are a bunch of things underneath of those categories. So broadly, what you're talking about is either a threat to internal validity or a threat to external validity. And I simply don't understand why what you said would be a threat to either one of those. So I'm just asking. But maybe we should take it offline and let someone else ask whatever question is on their mind.
So in last year's CCS conference, there was a paper on historical examination of open source releases and their vulnerabilities. So how does your work compare to those?
I think that in this paper, first of all, there are many papers. There's the Osman paper that studies the OpenBSD in a similar way. It's the Zamans that studies the Firefox. And then there's this. I think that it has complementary results with categories. And how the security category stands out when we perform the correlations between the two, the swarms that I mentioned. For the first one, the one that I mentioned first with the OpenBSD is they found that security bugs decrease over time, but they have a persistence of 2 years of bugs. And the second one, Zamans, they found complementary results with our correlation of size and threat counts.
So, I don't know if that answered your question.
Yeah, okay. That's a follow-up question though. So, since this workshop is on surprising or unsuccessful results, which category do you think your results were?
Non-results, neither increasing or decreasing.
Right. Do you think you did what you published in other venues because of that? Or?
I think that finding either, it's more surprising maybe. Non-results are not so handsome. I think that this was the right workshop to send me. No.
I was wondering, you took this massive amount of data and did one data analysis. Do you think there were some subsets that you could look at that you would be able to categorize, where you might be able to pull out some differences that might be associated with some quality of the particular application that you were looking at? Or would that be worth doing?
Can you give me an example?
I don't know, browsers versus something else, or I don't know, something.
Oh.
Something.
Categories of projects.
Yeah, categories of projects.
Oh, yeah. Yeah, this could be interesting in relation with another question that this research brought up. We found that there are projects with their own idiosyncrasies. Maybe a categorization of such projects would be.
Or the ecosystem of support project or something that might help to guide where a project might be more or less safe or reliable, or quality might be different.
Okay. Anyone else? Okay. Oh,
So do you see any implications for so-called Linus's law?
Yeah, I believe that for this result, the problem was with the ecosystem itself. So I don't think, that's why I mentioned it as an initial result, not as a further analysis. Your question has to do with? Sorry.
Well, Linus's law, as you put it, claims that with many eyeballs, all bugs are shallow. So does this provide evidence one way or the other on that from your perspective?
The result itself?
Yeah.
No, I expected that such releases would have a lower defect count. So
that didn't turn out to be the case. Is that
yeah.
right?
So this also shows that other releases might have trouble too. If you have the most the projects that with the highest beta, this could affect the other projects. They use code that is vulnerable.
So I mean, I personally think Linus's law is bogus. Okay, so
Yeah.
But I don't know, I mean, you didn't compare it to non-open source, so you can't say that it wouldn't be. I mean, I know, but what it did was all open source, so
Yeah, it's all
it all got the eyeballs. So we didn't look at the stuff that didn't have the eyeballs.
But the argument, I think, was the thing with more versions had
Probably more eyeballs.
Oh,
It didn't
okay.
turn out.
Oh, yeah, okay.
Yeah.
So you don't know how they do their versions though. I mean,
Right.
So-
There's many uncontrolled
Yeah.
variables.
Yeah.
Next speaker?